Long moving camera shots stand out because they help the audience engage with the action. But long takes usually need substantial time and money. In big budget filming, long takes need a whole camera team to work together. They rehearse their different roles. The crew members hold cameras, watch monitors, control focus, and mind each other's safety. But for every big budget production, there are 100 more where a single camera operator must do everything by themselves, or where the action is a one-off event. Camera operators often compromise safety to film the shot they want, but attention overload is quite common, because it's hard to watch a screen and watch where you're going. On the surface, the camera operator seemingly just needs a gimbal with automatic tracking, handheld or drone-based, that can adaptively reorient the camera to track a single target. That's where we started, but critically, filmmakers want control over what is filmed, and how it's framed, adapting to the scene as they go. We propose LookOut, a system for use in pre-production and on set. It can be used by a small team or a solo camera operator to capture long takes that require minimal post-processing. On a laptop, a person uses the LookOut interface to plan the camera behaviors vis-a-vis the actors. Then, on set, the exported script runs on a backpack computer, driving the LookOut controller during filming. The LookOut controller listens to verbal commands, talks back, monitors the video feed, and drives the now heavily modified $130 gimbal. At the start of filming, LookOut guides the operator through actor enrollment, where they point the camera at each named actor in turn, so that LookOut can train their appearance models.
Assign actor to dancer 2.
Dancer 2 first, yes, which is you. Alright.
Assign actor to dancer 2.
Through the GUI, a user chooses among camera behaviors and links them using onset cues that will trigger each behavior in turn. Behaviors can be looped or chained together to film long takes for as long as filming requires. The most basic behavior is framing of the actor. Here the operator can command LookOut to place the actor on the right place, or the middle of frame. Tight grip. LookOut confirms every behavior switch via text-to-speech, so there's no need for a camera monitor. Complicated paths, like this trippy side-to-side swaying, can be scripted in advance and triggered on set. With multiple actors, each one gets a name, and the behavior maps out whom to frame for each voice command. Actor A.
Follow primary.
Actor B.
Second actor.
Or both.
Both follow.
There are, of course, more than just these behaviors, but you can see the paper for more details or some of them in our video gallery. Now let's take a look at visual tracking. Visual tracking is an ongoing challenge. Trackers can be categorized by how well they cope with appearance changes over long durations, the number of tracks they can handle in one instance, if they are online, and how fast they provide updates. For example, SIMDWLT can track targets reasonably well, including in our use case, but it needs 500 milliseconds per frame per target to estimate location, so it doesn't work for latency-sensitive real-time control. This limits how fast a gimbal can react to fast-moving actors. On the other hand, DASIM RPN is a real-time, long-range, single-object tracker. But it more easily switches to tracking distractor objects, leading to temporary or long-term interruptions in the shot. Our method is different, and starts with the tracking by detection paradigm. The task is to find our actor in the middle of a sea of detections. This already gives us other detections for free for other potential actors or tasks. We build on existing trackers where a separate re-ID network produces appearance encodings for each detection. Data association is easier by keeping a gallery of such appearance encodings. We face two problems. The first is that for each actor, there's an incoming appearance encoding for each frame. Saving the entire history fills up memory, with 2,000 appearance encodings after just 2 minutes have passed. Also, these encodings are noisy, so could lead to momentary false matches, and those could pollute the gallery for subsequent use. Let's tackle the first problem. The default solution is to trim the gallery to just the last seen 100 encodings, or about 2 seconds. That's not ideal for long duration tracking, as our tracker could forget what the target looked like from other angles. Instead, we adopt a set of history management steps. We accept appearance encodings into history only if they are sufficiently different to what we already have. This only postpones the problem, however, and soon the gallery would be too big to match against quickly. We prune the history by randomly sampling encodings on every time step. While simple, this solution has two nice properties. The appearance history now trails off as time progresses, and it is cheap to compute. The second problem is handling noisy encodings. These encodings can make their way into an actor's appearance history when our actor overlaps with another person. To combat this, we only consider an encoding if the track doesn't overlap with other detections. Careful management of the history may not be enough. After an occlusion, momentary mismatches can easily occur when the system seeks to reacquire a target, and momentary mismatches can ruin a take. To remedy this, we built a recovery stage for finding a target after occlusion. In essence, LookOut validates a reacquired track by requiring good matches for every update during a moderate recovery period. We did try using existing tracking algorithms that scored at the top of the single object or multi-object tracking benchmarks. Even the longer videos among these benchmarks look qualitatively very different from typical TV and film scenes. So we manually annotated two very long videos that do represent our filming scenarios. Scores for those algorithms and our own new tracker are in the paper. The main finding is that some tracking mishaps are worse than others. For example, latching onto a distractor is worse than reporting loss of track, because it jerks the camera away, ruining the whole take, shown here with the red dot. Lighting conditions, occlusions, and distractors make it especially hard to film around other people. The unknown tracker used commercially in DJI's Osmo Mobile 3 needed 7 takes to get this sequence right, when ours worked both times that we tried it. Now that we have reliable tracks, let's turn to the controller. Our gimbal control drives the camera's orientation to behave according to the user's demands. Our design includes two cameras. The first is a guide camera with a 90-degree field of view. It feeds images to LookOut at 90 Hz at a native resolution of 720p. It communicates with our backpack over serial comms. The second camera is a star camera, capturing higher quality footage and with adjustable focal length. This allows us to decouple LookOut's scene understanding from stylistic filming preferences. We have control over all three axes of our camera gimbal assembly at around 60 Hz. While the operator has no screen, we can look under the hood of the core follow behavior. The user instructs LookOut to place an actor in a specific part of the frame. Here the user wanted the actor placed at the yellow dot, also shown at the bottom left in script info. We interpret a tracked actor's single on-screen location to be a point 20% from the top of their bounding box. At a high level, we achieve the desired framing through a PID controller that drives down the error, EFT, between some desired framing, P required, and where the actor or actors are at the current time step, P target. We approximate a linear mapping between actor angular locations in 3D to 2D locations in screen space. Horizontal errors in image space are corrected via gimbal yaw, and vertical errors are corrected via gimbal pitch. We tune the PID controllers to the limit of LookOut's control rate. However, if we use the raw noisy track locations from the tracker directly, our PID loop would produce erratic camera velocities. That would require detuning to reduce susceptibility to noise, sacrificing responsiveness. To solve this, we actually use a modified formulation for our error, ET. Instead of using raw track locations, we formulate an augmented track location, P-augmented. P-augmented is defined as the output of a common filter whose measurements are P-tracked. This common filter is unusual, in that its process variance is a function of how far P-augmented from the previous time step disagrees with P-tracked. The greater the disagreement, the higher the variance, and the faster updates are considered from the raw track location's P-tracked. You can see an illustration here. P-augmented is far from P-tracked, so the process variance is high, illustrated here on the bottom red bar and in the red on the ellipse. P-augmented moves to compensate and signals the PID controller to push a corrective velocity through the gimbal. We can define any function we want for this variance. We use a family of functions modulated by the radius of a simple ellipse. This ellipse defines how much movement an actor can get away with without triggering LookOut to reorient the camera on their account. A small ellipse means a tight camera follow, while a wide one leads to a more agnostic camera, only kicking in when the actor strays too far. This also works for multiple actors, with the augmented point trick allowing each actor to move independently within their ellipse. The final error is the difference in both x and y of both p-augmented and p-required averaged across all actors, which is akin to a Procrustes optimization when we introduce zoom. To allow for a smooth transition between actor framing behaviors, we weigh each actor's contribution with a time-varying factor, dependent on track visibility and script behavior switches. Here you can see the difference with and without these measures. This way we can get smooth responsive control and have an erratic camera be an optional style attribute. We can introduce zoom in our actor framing optimization or as a user controllable attribute, as in this example.
Close up. Zoom out. Half zoom.
This kind of control opens the door to all kinds of cool stuff. Here we introduce camera gimbal acceleration into the role of the camera frame, simulating handheld footage on a gimbal. We've validated the LookOut system in stages, from the bedrock of our tracker and control strategies up to the entire LookOut system as a whole, including the scripting interface and ultimately a critique of LookOut footage. The validation is split into three components: a validation of our tracker and control strategy, an end-to-end field study by filmmakers with variable skill levels, and a critique of LookOut footage by expert filmmakers. Please see the supplementary video on validation. We also include a gallery of LookOut footage in website form. The website has both star camera footage and guide camera footage, overlaid with LookOut telemetry so that you can inspect how LookOut reacts to dynamic filming. An explanation of these illustrations is available on the website. LookOut has been used for hours of filming. Novice users were able to film what they wanted, even while climbing, cycling, and skateboarding. Non-experts can easily become camera operators and still keep up with the action. LookOut handles the framing so the operator can keep it simple, or experiment, sweeping from up top, overhead, down to ground level, using the same script. Exceptionally, we can use other trackers to frame novel object categories. But for filming people, LookOut, with our tracker inside, can run smoothly, for an hour, over 2 kilometers, in a hilly desert. Overall, LookOut helps the solo camera operator stay safe, while getting the long takes they want. Thank you for watching.